Okay, so in this chapter, electromagnetism. So in this chapter, we talk about the combined effect of electricity and magnets, right? Before that, we individually discuss both chapters of magnets and electricity. And in this chapter, we discuss about the combined effect of electricity and magnets. So this is the topic which is related with the effect of electricity plus magnet, right?
Yes,
So before discussing about any formula, any equation, any application of this chapter, you need to know about the basic rule and the basic concept that what are the effect of magnetic field on electric field and what are the effect of electric field on magnets, right? Because if
yes,
there is interaction between electricity and magnet, so there will be effect of magnet on electric field and electric field on magnet. So let's first discuss about the first concept we need to know about is that magnetic field around a current carrying conductor. Magnetic field around a current carrying conductor. So this was the first concept of this chapter. And when scientists discover about this property, that it is possible practically that if there will be a current passing through a conductor, so with electric field there is also a magnetic field around a conductor. So if there is no magnet or there is no south or north pole placed around a conductor, only charges, or you can say that only current is passing through the conductor, so there will also be a magnetic field around that conductor. So that was the natural phenomena, right? So we need
yes,
to know about the direction of magnetic field and how magnetic field produced around a conductor. So you need to know about their direction and their properties, right? And same goes for the magnetic field. When there is a magnetic field and if you move a conductor between magnetic field, so there will be a value of induced EMF in a conductor. So you first need to know about these two concepts. Then we will discuss about the combination of electricity and magnets, and there will be a new quantity on a conductor which is known as force on a current carrying conductor in a magnetic field, right?
yes,
So for demonstration, let's see that how it is possible practically. Okay, check out the practical explanation of this concept. Talk about the direction and the property, right? So
yes,
know that how it is possible. Okay, in this experiment, there are multiple components, right? One is a conductor, and there is also a power source, There is also a rheostat connector and some iron fillings are there, because normally we use iron fillings to identify the direction or the force of attraction by magnet, right?
Yes.
So let's first check out the complete experiment.
Sprinkle iron filings around the conductor. Insert the plug key and observe. We can observe that the iron filings are aligning in a pattern of concentric circles. These represent magnetic field lines. Let's place the compass over these lines. The direction of the north pole of the compass represents the direction of these magnetic field lines. By moving the compass over the lines, we can see the direction at each point. By moving the compass away from the
Okay, in this experiment, you observe that first iron fillings are in random position or in random order, right? There is no fixed pattern, no fixed shape over there. And when you turn on the electric current through the conductor, so there will be a magnetic field around the conductor. So that's why iron filling will arranged in a circular pattern, right?
Yes. Where
And
is the magnet?
this is the concept we are studying in this chapter, that we can also produce magnetic field without magnet, right? But for that purpose you need to have a conductor with a value of electric current passing through the conductor, right? So there will be also a magnetic field around it. So this is the practical demonstration of that experiment, that how is it possible. So that is practically proven and scientists already discovered this phenomena. So you don't need to explain the theory behind this concept. You just need to know about the practical application of this concept, right?
Yes.
Okay. So now you can see that the iron fillings are now in a circular form. And in magnets, we know that magnetic field flow from positive to, sorry, from north to south pole, right?
Yes.
So now we need to identify the north pole first, then we can easily identify the south pole. Okay.
Mhm.
So for that purpose, we use compass to identify the direction of north. And you can see in the diagram that north direction is clearly visible. So what will be the direction of magnetic field? Clockwise or anti-clockwise?
It's anti-clockwise.
Anti-clockwise, right?
Yes.
Okay. So if current is passing in one direction, so there will be a clockwise rotation. And if current is passing in the opposite direction, so current will be in opposite direction. Magnetic field will be in opposite direction. So that is the concept, right? Now let's
Yes.
see that how we can identify the direction of magnetic field around a conductor, because in your exam, in your paper, we are not going to use compass and iron fillings in our exams. We need to know about the rule or some equation or some formula to calculate or to identify the direction of magnetic field, right?
Yes.
So if you want to identify the magnetic field around a current carrying conductor, so let's suppose if there is a conductor, first we consider a simple vertical conductor, right?
Yes.
And around it, there is a paper, right? And on paper, iron filings are there in random order.
The
And now
green color thing. The green rod is the conductor, yeah?
Conductor, yeah. And let's suppose the direction of current is in upward direction, right? Current is flowing in upward direction. Okay.
Yes.
So now we need to know about the rule that how we can identify the direction of magnetic field. So to identify the direction of magnetic field, we can use right hand rule to identify the direction of magnetic field. And right hand rule can be used in such a way that you need to hold a conductor like this, that your fingers will curl the conductor, right?
Yes.
And your thumb must be in the direction of electric current, right?
Okay.
This is the direction of your thumb that will indicate you the direction of electric current, and the curl of your fingers represents the rotation of magnetic field or the direction of magnetic field, that either they are clockwise or anti-clockwise, right?
Okay.
So
So
you can
the
use your pen or
mm,
pencil as a conductor and you can choose any direction of electric current. Let's suppose if you hold your pen with the same orientation given in the diagram, so you come to know that the direction of the magnetic field is clockwise or anti-clockwise. So the
is
direction
there it's from north to south or south to north?
direction of magnetic field is always from north to south. We just need to identify the direction, that either the north field is flowing in the clockwise direction or in anti-clockwise direction, right?
Yes.
So if you hold the conductor like this, so rotation will be in this form, right? Is
Yes.
it clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise, right? So
Yes.
thumb represents you the direction of current, which is in upward direction for this experiment, and the finger curl represents you the direction of magnetic field, right?
Yes.
And magnetic field is in anti-clockwise direction, right?
Yes.
Okay. And if current will flow in downward direction, so what will be the direction or what will be the rotation of magnetic field? It's clockwise, right?
Yes.
For that purpose, you need to invert the position of your hand in downward. So thumb will indicate in downward position. So the rotation will reverse and that will become clockwise, right? So this is the rule, right hand rule, or you can say that this rule is discovered or invented by Fleming. So we can also call it Fleming's right hand rule, right?
Yes.
So if you want to identify the direction of magnetic field, so you can easily identify with the help of right hand rule. So thumb will indicate the direction of electric current and the finger curl give you the value of or the direction of magnetic field, right?
Yes. Can you explain me the part of magnetic field is equal to anti-clockwise and why clockwise?
Because conductor is in vertical size, or you can say that is in a single axis, so that's why field will generate around the conductor, because the conductor is in circular shape or in circular form, so that's why field will also generate in the circular form. Let's suppose if the coil is in a circular loop, or you can say that if we make a loop with the help of a conductor, just like the example of a spring, So this is the first orientation or the first condition. Second condition, if we take the conductor like this, okay,
Yes.
so this will be the direction of, sorry, this will be the new orientation of the wire that is now in a circular form. So now how we can use the right hand rule to identify the direction of magnetic field.
By holding a wire
Okay, now we need to hold a wire in different manner because now there will be not a single direction of electric current, right?
yes.
So that's why you need to change the orientation. So how we can change the orientation? We can change the orientation like this. Now you can hold the wire like this, that your finger curl will be, let's suppose
on the back.
current, yes, current will flow from positive. So current first move in upward direction, then in downward, then from the back side upward, from front downward, from back upward. So you can imagine that how this current will circulate into the coil, right?
Yes.
So by holding,
We can stretch the wire.
yes. So now you can hold the wire like this, that your finger curl will be in the direction of the circular form of the wire, right?
Yes.
So your finger will hold this conductor like this, and the direction of thumb will be towards
The negative side.
this side.
Mm,
Okay. So if current is moving from back to forward, yes, so the direction of the thumb will be towards
both
negative side
sides.
like this. So current will move upward direction from the back and downward direction in the front. So the orientation of the hand will be like this. And now the indication of the thumb and fingers will be different because now thumb is not in the direction of electric current. Basically, thumb represents the direction of North Pole, right?
The thumb represents North Pole in this diagram
Yes,
or
in
like
this
in
diagram.
everything.
When the coil is in circular form, so you can use the direction of thumb to indicate the direction of North Pole, right?
Mm,
And the direction of, or you can say that the finger curl represents you the direction of electric current, right?
yes.
So that is the difference between two orientation of coil. Either the conductor is in a straight line or either conductor will be in a circular form, right?
Mm,
Okay. So this will be the direction of magnetic field and electric current in a current carrying conductor. Okay. So important concept from this whole diagram is that magnetic field can be generated with the help of,
electricity.
yes, with the help of current carrying conductor or electricity or charges passing through the conductor, right? So this is the important concept we learned from this diagram and from these two different orientations, right?
Yes.
Okay. So now move towards our next topic or our next concept, that is the reverse of this concept, that we can also produce, or you can say that we can also induce EMF with the help of magnetic field, right?
Yes.
Okay. So now let's see how is it possible. Let's first see the practical application, then we will discuss about the direction. Okay.
Yes.
Induced EMF. Okay, so this is the practical application.
Electromagnetic induction by changing the magnetic field around a conductor. We have taken a bar magnet, a coil, and a galvanometer. The galvanometer is connected to the coil and is used to detect the current flowing in the conductor. Move the magnet into the coil and carefully observe the galvanometer deflection. As the magnet is moved near the coil, there is a momentary deflection in the galvanometer. As the magnet comes to rest, the deflection of the galvanometer stops. The deflection of the galvanometer indicates that there is some current flowing through the coil. The galvanometer deflects only when the magnet is in motion near the coil. Motion of the magnet is responsible for the changing magnetic field. This changing magnetic field is inducing the current in the conductor. This phenomenon is called electromagnetic induction.
Okay, so this is the concept. You can see that when you move this
To detect
magnet
the
forward or backward, so when magnet is in a still form or in rest state, so there will be no electric current, or you can say that EMF through the wire. But when you start moving the magnet in forward or backward direction, so there will be an induced EMF, or you can say that there will be a value of electric current or a voltage in the coil, or you can say that there will be a charges now moving in the coil. So that's why there will be a deflection in galvanometer, or we can also use ammeter to find out the deflection or the movement of charges in the wire or in the conductor. Okay, and you can see that when you are moving the magnet in forward direction, so deflection will be different. Yes, you can see that.
Why does this happen?
And this happens because when magnet is in rest state, right? So there will be a uniform magnetic field passing through the coil, right?
Yes.
Okay. And second, when you move magnet in forward or backward direction, so the magnetic field in the coil is changing, right? And we already
Yes.
know that there will be effect of magnetic field on electrons, and there will be also effect of electric field on magnets, right? So both will affect each other. So that's why due to change of magnetic field, there will be a value of induced EMF, or you can say that there will be a value of electric current or voltage that can be produced without any connection or without any electricity or without any power supply, right? You can see that in this circuit there is no battery, no cell, no power supply is connected. Electric current is only generating with the help of this magnetic field, right?
Yes.
So this is the concept, right?
Mm. Yes, yes.
Okay. So this is the second concept, that you can also produce value of electric current with the help of magnetic field, right?
Yes.
And let's suppose if there will be a coil, sorry, if there will be a straight conductor, right? So that can also be possible, and not happen only in the circular wire. Now you can see that there is a north and south pole, and these lines basically represents you the magnetic field. And now you can easily move conductor around the magnetic field. And when magnetic due in the magnetic field, when conductor is placed at a fixed position, so there will be a fixed value of magnetic field passing through the conductor. And when you start moving the conductor into the magnetic field, so due to the change of magnetic field, there will be a disturbance in the motion of electron, and that will produce the value of EMF or electric current, right?
Yes.
Manometer that will detect any passage of electric.
Yes, you can see that. When you move down the conductor, so there will be a flow of charges, right? That can be observed in the galvanometer. And when you move up this straight conductor, so there will also a flow of charges in the galvanometer in opposite direction, right?
Yes.
And now you can see that when you are moving in a horizontal line, so there will be no change in magnetic field, right? So that's why there
Yes.
will be no electric current like this, because the value of magnetic field is constant over there. So that's why there will be no electric current. These are the point. The metallic conductor wire cuts the magnetic field lines of the magnet, causing an induced current in the wire, right?
Yes.
So that will produce the value of induced EMF, right? So that is another concept which is related to electromagnetism. And that second concept is like this. The main heading of this topic is induced EMF, and the purpose of this concept is, and the definition of this concept is, so the concept of induced EMF is like this. EMF will induced in the conductor when we move a conductor in a magnetic field. So due to change in magnetic field EMF will induce, right? We are using the word induced because there is no direct connection of electricity or any power source with the conductor, right? This EMF is
Yeah.
generating due to the change of magnetic field. That's why we are using different term which is known as induced, because induced term is used only for that purpose when there will be no direct connection of any source or any cell or battery with the conductor or the wire, right?
Yes.
So these are the two important concepts of this chapter. And next we will start with the topic of force on a current carrying conductor in a magnetic field, right?
Yes.
So at what time you will be available on tomorrow? Is it possible in morning or
After 3 o'clock.
okay? So we will continue with the topic of force on a current carrying conductor in a magnetic field tomorrow, right?
Yes.
Because first you need to know about the whole concept, then we will continue with the applications and the formula of this chapter, right?
Yes.
Okay.
So these all which we just studied are the basic concepts of the chapter.
Yes, because first you need to know about